So this leads to one hypothesis, which is, do perceived inequalities generate some antagonism in a society? And this antagonism leads to polarization because people have distrust between each other and will take opposite views on various issues. So this is this hypothesis that we would like to test in our model, in one model. And our approach is to design a theoretical opinion model that explores this hypothesis. So this model is very simple. We have identical agents that are fully connected. We study it for the moment with a low number of agents, 20, 40, not more for the moment. And we would like to study only the randomness, the effect of the randomness of the interactions that will bring possibly some distrust between the agents. And we would like to connect this to the inequalities of between the agents. So the model state is can be represented as a matrix. So let's consider this is me on the line. We will have my opinions about the others. Here we have NA agents. My opinions about all the other agents will be on the line, the horizontal line here, M. And the opinions about me, of the other of your opinions, or for instance, your opinions about me will be on the column here. And one of your opinions will be on this line here, Y. And the opinions about you will be on the column here, on the column Y. So here, for a population of NA agents, the model state is n squared opinions. So here we have, you see that each agent, whether me, I have an opinion about myself, and you have an opinion about yourself as well. So this is, and we'll see that the fact to have an opinion about each other, about oneself, is very important in the model. So we have random pair interactions. The dynamics of the model, like we've seen the state, the dynamics of the model is to draw at random pairs of agents, me and you. And at each time step, each time we draw one pair, I will, let's say this is the pair me and you, we will interact together. So you will influence my opinions, and more precisely, you will influence my opinions about myself, my opinion about yourself, and possibly the opinion about K other agents that you're talking about to me. And I will do the same. I will talk about myself, about you, and about other agents, and this will modify your opinions about these agents. So how does it modify, how do the opinions, how are the opinions modified? So if you talk to me about agent J, whether it's me, you, or someone else, I will modify my opinion about this agent. With here you have the equation. This equation means that I will be, this is a very standard type of dynamics. I will be attracted by your opinion. So you will attract, my opinion will tend to go a bit towards yours, but with some variations. The first variation is that I don't have an direct access to your opinion. I may be wrong in the interpretation of what you're talking to me. So I may have a view of your opinion that does not reflect exactly your own opinion. And this will be accounted for by some noise. This is the value theta of t here that will be drawn, and theta of t is drawn, we assume, uniformly between two values, minus delta and plus delta. So my opinion, when we are talking, is not attracted directly by your opinion, but by your opinion with some noise, some mistake. This is the first point. And the second point is that if you are very important to me, if you are someone that is, let's say, very important in the scientific community, your Nobel Prize, for instance, then your opinion will be very important to me. And what you will be talking to me will have a great impact on my opinion. Whereas if you are someone that is much less important, and for instance, I don't think what you're doing is very good, and so on, I have a bad opinion about you, then your influence will be small. And this is modeled by this, the function of propagation, which is P of my here, and which expresses that if my opinion of myself is much higher than the opinion I have about you, then I will give you a low importance. Your influence on me will be small. On the contrary, if I give you a high importance, and compared to the importance I give to me, then your influence will be high. This is a classical logistic function. So to summarize, when we discuss together, you will express your view, your opinion about me, about yourself, and maybe about some other people. And this will modify my opinion about myself, about you, and about these other people. And I will do the same. I will tell my opinion about you, about myself, and maybe about other people. And this will modify your opinion about me, your opinion about yourself, and your opinion about these other people I'm talking about. So the model has three parameters. So the sigma, which defines the shape of the propagation function, delta, which is the level of noise. Remember, the mistakes are drawn uniformly between minus delta and plus delta. And K, the number of agents we are talking about each time we discuss together. And K can be 0, of course. In this case, we don't have gossip. In the following, we have chosen some values for these parameters. You have them here. So now I will show the main patterns of the model. I will show the pattern without gossip. So when K equals 0, so when we discuss together, we're talking only about ourselves. When we add gossip, what's going on. And then I will show the pattern with a model which is a bit modified, in which we actually limit the inequalities between the opinions. So what are these patterns? First pattern, when we have no gossip. So when we meet together, we only talk about me and about you. So what happens in this case? You have on the left, each line here is the evolution of a reputation. A reputation is in the matrix. This is the average in a column. Here in this example of the matrix, here you have the state of the matrix I've shown before after 1 million interactions. And you can notice that in this matrix, the columns tend to be similar. The values in columns tend to be similar. This means that the agents tend to agree on their opinion about each other agent. And this is not surprising because we remember the dynamics tend to attract, the opinions tend to attract each other, even though there is some noise, which explains why the columns are not exactly identical because of the noise, but they tend to be similar. And here, so we represent how this average of each column evolves over time. And you can see that most of the column go to the top and they have big variations. And this is reflected on this example of matrix. You see that most of the columns are red, and red corresponds, I didn't tell it, it corresponds to the highest values of the opinions, which are close to +1. I didn't tell something which is very important. The opinions are limited between -1 and +1. And what you can see on the left also is a red curve. And this red curve is the average of opinions. And so you can see on the left, the average of opinions. So if you make the average of all opinion of the matrix, tend to grow over time and then to stabilize on a plateau. So in this case, we have quite a surprising result at the beginning. When we first made the simulations, we were surprised by this result. The average opinion tends to go up. So this is the case I was referring right at the beginning. Here you are in the case where when people discuss, they tend to have a higher and higher opinion about each other. So this is a kind of ideal world where people tend to appreciate each other over time. And this is surprising because we'll come back to this, but if you look at the equation at the first glance, there is no asymmetry. So we could, no obvious asymmetry. So we could expect that the average opinion would remain close to 0 if we start at 0. There is no obvious reason why we have this asymmetry that drives the model towards positive opinions. So now let's look at the typical pattern. When we add gossip here, we have k equal 5. It means that when we talk to each other, we talk also about 5 other people we know. And you see here that the pattern is very, very different. Here again, you have the evolution on the left, you have the evolutions of the reputations. So we have wider variations of the reputations, and you see the density of reputation is higher for low reputations, negative reputations. And this is also illustrated by the matrix, which is an example of what happens after 1 million interactions. And you see that even though you have positive red reputations, most of the reputations of the columns are blue, meaning that they are negative. And this is what we can see on the left picture. And we have another evidence of this negative tendency with the average opinion, which is in red. Here we see that the evolution of the average opinion is mostly negative. So when we add gossip in this model, we observe strongly negative effects. So in this case, we have a group where, because of the interactions, initially all the agents were had zero opinion. They didn't know each other. But with the interaction, they tend to have negative opinion about each other. So we have here a group that has negative tendencies and some antagonism within it, because people tend to not appreciate each other. And finally, the last typical pattern. So here, this is the case I was mentioning before, where we artificially limit the inequalities between the opinion. And to do that, we artificially modify all of the opinions towards their average of the moment at time t, after having a certain number of interactions. We take all the opinions and we drive them a little bit towards the average of the current average of the opinions. So not surprisingly, the reputations do not oscillate as much. So the differences between the opinions and the reputations is smaller, of course, because this is what we have done artificially. But the effect of that is that the average opinion is increasing steadily and after remains very high. And this is illustrated on the right with the matrix, which is almost red. So in this case, when we have reduced the inequalities between the opinions over time, then we have opinions that are growing. So we have a society or a group, let's say, not a society, that where everybody loves everybody. So this is the ideal case. So reducing the inequalities in the group drives to people who appreciate each other a lot. So this is something, an ideal group where people, everybody loves everybody. So now we will try to explain why we get these results. So we have tried to make a theory of what's going on.
Мы пробуем создать теорию о том, что происходит.
The principle is to try
Теоретический эффект будет попробовать использовать модель, среднюю модель над шумом и над взаимодействием.
The noise that happens at each interaction, and also we have the randomness of the history of interactions. I can discuss with one person and after another, and maybe a third one. And if the order is different, the result is different as well. So to have a general perspective on what's going on, we are trying to make a theoretical model that average over all these sources of uncertainty, of randomness. And we'll do it first with a very specific case, simplified case of two agents. And we'll show that considering two agents, there is a positive bias on self-opinion that appear, and a negative bias on the opinion about others that appear. And I will explain what it is. And then, with the same approach, we will model the average reputation without gossip. So the average, again, over noise and interactions. And the average reputation with gossip here when considering any number of agents. Okay, so let's start with the case of very simple to have an intuition of what's going on. So this is, there are two agents, me and you. And we even simplify the problem by assuming that your opinion about me is fixed. So it doesn't change. So let's say your opinion about me is value B. And my opinion about you is also the same, B. So the opinions about you are fixed, and your opinion about me is fixed also. And let's say your opinion about me is A. So these opinions do not change over time. The only opinion that changes is my opinion about myself within this model. And we assume that at the beginning, my opinion about myself is the value A, so the same as your opinion about me. And we'll simplify the notation, and we call M of T the difference between my opinion about me and this initial opinion. So this is the change compared with this initial opinion. So we'll try to see what's going on at the first step. So we have a first interaction, and in this first interaction, your opinion about me doesn't change. So the only source of change is the mistake I make about my interpretation of your opinion. And this value is of T, which is the noise that is my mistake, modeling the mistake I make on the interpretation of your opinion. And we call H the inference I give you. So at the first step, we apply the equation, and we find that actually my opinion about myself is varies linearly with this noise and with the coefficient of the inference I give you. Therefore, if we make the average over the noise, as the noise is centered, this is a uniform noise between minus delta and plus delta, the average of my opinion about myself at the first step is 0. However, if we consider now the second step, we apply again the equation. So we have another, I have another interaction with you, and I make another second mistake about what you think about me. So the second mistake is theta of 2. And now we make a development of the first order of the influence function, the propagation function. So h at the moment of the interaction at time 2 is approximated by h plus the derivative of h prime multiplied by my opinion about myself at this moment. And if we apply the rule of interaction again, then we see that the only term for which the average is not 0 is the term in red here. And this average, if we make the integral, is this value here, which is positive because we remember that the function h, function of influence, decreases with the opinion. When my opinion about myself increases, then the influence I give you decreases. So we have value at the second step, an average value of my opinion about myself at the second step, which is slightly, because here we have a term which is in the second order. This is delta square. So my opinion about myself at the second step, it's on average a bit higher than the opinion you have about me. And so we can test, compare this theoretical result with the simulation. Here in this curve, in this graph, each dot is the result of several million simulations. And the line is the model. So this is the value I presented before. And here in this case, so this is the value of my opinion about myself for different initial differences. So B is 0. And this is what we have here is the value of A. So the opinion I have about you have about me. So, and we see that the difference between my opinion about me and the opinion you have about me, I will have my positive bias about my self-opinion will be the highest if my opinion about you is slightly above my opinion about me, my average opinion about me, or your opinion about me. So to give you an intuition of what's going on, let's assume here, this is the starting point at my opinion about myself is 0 at the beginning, and this is the opinion I have about me as well. But assume that at the first moment I make a mistake, and I think you have a lower opinion about me. So my opinion about me will decrease. But when my opinion about me decreases, I give you more influence. So at the next step, when you will have, we'll make a mistake in which I will think you have a better opinion about me. Since you have a higher influence, my opinion about me will go up easily. Whereas if I have at the beginning, my mistake makes me think that you have a better opinion about me, then I'll give you less influence because I'm more confident. And then when you have an opinion that it will be, my mistake will be, I will make a mistake, will make me think that my opinion about me is lower, then my opinion will about me will decrease less easily. So in a way, you see, I have to go up the hill, so it's more difficult, whereas previously I had to go down the hill, so it was easy. So that's why my opinion about me will tend to be a bit higher on average. So going down the hill is easier than going up the hill. So on average, it will be a bit lower than the average opinion here, than your opinion, you have about myself. So this is a surprising phenomenon. I tend to have, in this context, I tend to have an opinion about myself, which is a bit higher than the opinion you have about me. Although the noise, which is important, the noise is centered. There is no bias in the noise. The bias comes from the fact that the influence function is decreasing when my opinion about me increases. And similarly, we have a negative bias on the opinion about others. Now we are considering another very simple case where now I am talking with you and I have my opinion about my mistakes, and this is your opinion about me, which is changing. So when we discuss, I have always the same opinion about myself, but you make mistake about this opinion. Your opinion about me will change because of these mistakes. And we do the same computation, and we see that in this case, we have your opinion about me will be a bit smaller than the opinion I have about myself. Here, because you remember h prime here, this is the same as before. So the derivative of the influence function is negative. So this is why this value is negative. And intuitively, so yeah, we can have here the same checking of simulation with this average value. And to understand what's going on, this is the same phenomenon, except here. So here, this is your opinion about me, whereas before we had the opinion I have about myself. And what's going on is that you make mistake about the opinion I have about myself, and if the mistake is up, so you think my opinion about me is higher, then you will decrease more easily because you go downhill than if your mistake is down, where it will be more difficult to go up. So as a result, in this case, the average opinion you have about me will be lower than the opinion I have about my self-opinion. Okay, so with this first simple example, we have this idea of the methods, so averaging on the noise. And we have a first example of asymmetry in a way, which comes from the slope of the propagation function. Now we complexify a bit the theoretical approach. We're considering that I discuss not only with you, but with many people, many different people. So here, discuss with NA agent -1. And again, to simplify the problem, we assume that only the opinions of these people about me are changing. The other opinions, the opinions about the other agents are fixed, and we call them BI. So the opinion about agent of index I are called BI, and they are fixed. And again, we assume that my opinion about myself at time 0 is A, and this opinion is shared by all the other agents. So in other words, at the initial state in the matrix, all the columns are, all the values in the columns are identical. So everybody agrees of their opinions about each agent in a column, but the columns are different. And we developed a model that approximates the average evolution of what we call M of t, which is the difference between the opinion I have about myself and my initial opinion. So we'll, if we assume that the initial opinion is 0, then this is the opinion I have about myself over time. And the opinion you have about me, all of you, over time as well. And we developed a model that allows us to compute this value over time. I don't go into the details because there are several equations that are a bit complicated. I will focus only on the case where here, which is a bit simpler to present, but uses these results. We're considering the reputation, my reputation over time. And my reputation over time is the average of the opinion I have about me and the opinions you have about me over time. And more precisely, what we managed to compute is the difference at each time step between the opinion, the reputation, my reputation at time t+1 minus my reputation at time t. So we call it delta reputation, and this delta can be put into the sum of two terms, delta 1, which is the change of reputation of first degree, and the change of reputation of second degree. So let's see what is the change of reputation of first degree. You see here, you have a sum where you have differences between my opinion about myself and your opinion about me. And here you remember, since I have a positive bias, my opinion about myself will be higher than the opinion you have about me, and your opinion you have about me will be lower than the opinion I have about me. So here, these differences here are positive. And here you have a coefficient, and this is the influence. So if I give you a large influence, then this coefficient is close to 1, and here we have a negative coefficient. So here, if I give you a large influence in this sum, your influence on my reputation, your change on my reputation will be negative. And if I give you small influence, then your change on average, the interactions with you will give an increase to my reputation. So here, the second term here is multiplied by the derivative. I will not insist. And here, this is a term of second order. So here we have the square of my opinion, and the difference between the square of my opinion and the square of your opinion. So let's see a connection, just to make a connection, an intuitive connection between this result and what we've seen before with two agents. We can, at t equal 2, recognize here the reputation. It's equal to the delta 2 reputation at time 2, because at time 1 the average reputation is 0, and the delta 1 is 0 as well. And if we compute, if we write down delta 2, then here in blue you recognize the negative bias when there is an interaction of two agents, when I have a single interaction with you. So this is the negative bias that we've seen before when we had interaction between only me and you. And here we have a sum which is an average where we can recognize the positive bias also when we have an interaction between me and you, but also other positive bias that are crossed between me and other people. So there is an intuitive connection between, we see that the positive bias and the negative bias that we've seen before have a role in this evolution of the reputation. But of course, when we increase T, we have much more complicated values, and it's more difficult to recognize this positive and negative bias. But what we can see, if we make the simulations, here we have a case, simple case with 5 agents, and we initialize the matrix with reputations going from -0.3 to 0.3, and they are uniformly distributed. So we have these starting points here, and on this graph you have the evolution of the change of these reputations. So beginning this is 0, and you see that after a while they stabilize. So this is interesting. This is the change, the delta. Here, this is the delta reputation for each reputation, initial reputation. So we have 5 curves. And for each, assuming that the others do not change, the opinions do not change. So these are the lines, and the dots that we see here are the evolution of the reputations on the average evolution for 100 million simulations of 30 steps. But here, considering this data simulation where everything changes. So it shows that our approximations fit well the average of 100 simulations here. This is the first point. And the second point that I would like to show here is that the change or after a while is stabilized. So it means that the evolution of the reputation, if this change is positive, like here, the evolution of the reputation will keep increasing with the linearity time. And when it's negative, like here for reputation 0.3, the delta reputation is negative, then it means that the reputation will decrease linearly over time. We can do a similar. We can use a similar approach when there are gossip, and there is gossip. It can be shown that there is a new term that appears. This is here. It's a term of first degree, which looks a bit like the term of first degree when there are no gossip. But instead of the difference between my opinion and your opinion, these are differences between opinions of the people that are not me, other people than me. Again, when we make simulation in a similar case as previously, then we see that the change of reputation stabilizes over time. And we observe also that the model fits quite well the average of 100 million simulations. Now we use, since we have this stabilization, we can use this theoretical model to study what was our purpose from the beginning, the effect of inequalities of reputation on the evolution of reputations. So we will look at this change of reputation after a while when it stabilized. And we'll watch also the change of reputation of first degree, second degree, and first degree when there is gossip. When we change the initial level of reputation inequalities, and we'll do it in case there is 20 agents without gossip, 20 agents with gossip, and 40 agents without gossip, 40 agents with gossip. So here we represented on the x-axis, you have the inequalities. So the inequalities are measured as the difference between the highest and the lowest reputation. For instance, here this is 0.2, here 0.4, and so on, 0.6, 0.8, 1, 1.2, and so on. So these are the differences. Here you can see you have the 20 points here represent the starting point of the reputations, and the lines represent the evolution when the change of reputation when it's stabilized. So what we can notice is that when the inequalities are small, here you have 0.2 difference between the highest and the lowest. We see that the evolution of the reputations are all positive, and they are all positive until a given level of reputation inequality, where you begin to have the agent of lowest reputation, which has a reputation that decreases. And the number of agents which have the reputation which decreases is increasing with the reputation inequality. So we see here that this corresponds to our hypothesis, which is that when the reputation inequality is high, it has the tendency to increase. And you have a larger and larger number of people here for which the reputation is decreasing. If we try to understand why, with the two terms, the term of first degree, we see that the term of first degree, this is the same representation, but using only the delta 1, so the delta of first degree, tends to increase the inequalities. The high reputation tend to increase, and the low reputation tend to increase. And what is noticeable as well is that you have, this is not totally symmetric, this is broadly symmetric, but not completely. You see that for low reputation inequality, the high reputation tend to go up more quickly than the low reputation go down. So for low reputation inequality, the asymmetry is in favor of positive, of growing reputation. Whereas if you are considering high inequalities, then you see that here the reputation is decreasing more than the opposite one. So it means that when the inequalities are higher, the asymmetry is in favor of decreasing the reputations. So when the inequalities are growing here, the effect of delta 1 is to increase the inequalities, but in favor of and decreasing more the low even more the low reputation than the high, then it grows the high reputations. The term of second degree has the opposite effect. It also seems broadly symmetric, but it's not exactly the case. You see that here in the low inequalities, you have a strong asymmetry in favor of positive move, so in favor of growing the reputations, the low reputations. It grows more the low reputation and it decreases the high reputations. And this is less true when the reputation inequality increases. So the difference decreases. this explains the whole result. So now let's consider the same graphs, but now with gossip, still with 20 agents. So again, you see that when the inequality is very small, all reputation tend to increase, but we have similarly, but more blue here. So we have more cases where the reputation decreases. And we can compare more directly. Here you have the two graphs that are overlapped, superposed. So, and in the dotted lines correspond to without gossip. So we see that the dotted line tend to go up more than the solid lines. And we have red dotted lines, which correspond to the case without gossip, whereas with gossip, we have blue lines. So we see that, not surprisingly, given the patterns that we have observed, the threshold when you have gossip, where you're beginning to have increasing inequalities, is smaller. So you need a very small inequalities to keep all reputation going up. If we consider the change of first degree, then comparing with a case, again, without gossip, we're seeing that with gossip, the increase of inequalities that is driven by the delta of first degree is higher. So when there are gossip, the increase of inequalities is larger, and the decrease of inequalities, the terms of second degree, is smaller. But we have this additional term, which is the first degree for gossip, that counterbalance a little bit. It's tend to decrease the inequalities. So it plays a role which tends to moderate a bit the increase of inequalities. Just a similar graph in the case of when we increase the number of agents. Here we have 40 agents. And we can see here that previously with 20 agents, the increase of inequalities was starting with threshold of inequality, which was 0.8, whereas here with 40 agents, 0.8, every agent is growing. There is no increase of the inequalities. So it seems that without gossip, when you add agents, you tend to increase the solidarity among the group. But it's not true with gossip. With gossip, we don't see the same difference. Okay, I summarize. In the model, so beyond a threshold of perceived inequalities, the inequalities tend to increase. Low reputation tend to decrease, and high reputations tend to increase. When there is gossip, this threshold of inequalities leading to an increase of inequalities is smaller. And when the inequalities are even bigger, we can't have a majority of reputations that tend to decrease. This is the case where the whole opinions tend to be more negative. So we are in a world where there is a lot of hostility, antagonism in this case. So to summarize, reducing perceived inequalities, whether you have gossip or not, below a given threshold, tend to increase the perception everybody has about the others. In the model, I'm not claiming this is exactly what's going on in reality. So the limitation of the model. So the model is limited to a very small group where, more crucially, everybody discusses with everybody. And we have to check if other dynamics and heterogeneity between agents, also here, all the agents are the same. These heterogeneities that are not included in the model could have bigger effect that would annihilate, erase, neutralize the effects that we have observed here. The perspectives, so we have several perspectives from this model. First, extending the model to larger population and introducing possibly other processes. In particular, we are interested in introducing a process which is connected to group identity, which could reduce this perception of inequalities. We are also involved in performing lab experiments that check some predictions of the model, in particular the positive bias on self-opinions when there are interactions between the two agents, and also negative bias in opinion about others. And finally, there is another perspective that I think is opened by this study, which is that we see that the gossip, the effect of gossip, the negative effect of gossip can be quite important. And I'm wondering if the type of dynamics of gossip that we have on social networks could have an impact, a particular impact. So I think that there could be interesting studies on gossips within the social networks related to this. Thank you for your attention. Now I'm happy to discuss and discuss about your points and questions. Thank you very much.